Okay, good morning, everybody. I'd like to thank organizers to giving me this great opportunity to present my recent research, and also thanks for organizing this such a nice conference. And I'm very excited because I always, all the people, I always read paper of your name. So I was a little bit too excited and prepared too much slides. So maybe some of them were skipped. Okay. So in this talk, I'd like to introduce you the multiple order of 5D transition metal oxide in insulating compound and also metallic compound. And the first topic is on this barium 2 magnesium rhenium O6, as already discussed double perovskite compound. And I'd like to talk about how I detected quadrupole order in this compound. And also talk a little bit about pressure and chemical pressure effect on this compound. Then on the next topic, I talk about this special pyrochlore metallic oxide. And this compound is really special and shows very complex structure transition. And this crazy structure transition can be interpreted as multipolar order in itinerant system. Okay, this work has been done with my, I'm a solid state chemist and crystal grower. So I'm mainly synthesizing compound with my previous research group and my current research group. And, and we are working with the synchrotron diffraction experiment experts. And nowadays, we are collaborating with scientists abroad, like Ivica in the audience. And yeah, and now we are supported, theoretically supported our work. So let me start from this particular double perovskite compound. And first, let me just remind you what's the difference between the electronic state for D5 and D1. So both of them have spin 1/2 state and effective orbital angular moment of 1, but this is more than half and more than half field, and this is less than half field. So that's entangles spin and orbital moment differently. As a result, you have J 1/2 state. This is a very important ingredient for Kita F spin liquid. But for this case, we have J 3/2 state with 4-fold degeneracy. And this degeneracy gives rise to multiple degrees of freedom. Actually, the multipolar order physics have been already established in 4 f-electron systems. And serum B6, this compound is prototypical and representative compound that shows quadrupole order. And interestingly, the ground state, the 4-fold degenerate gamma 8 ground state is identical in terms of symmetry as J 3/2 state. So from this state, people knows we gonna have dipole, quadrupole, and octupole moment. So this kind of 15 possible octupole can be realized from J 3/2 state. So, as far as I know, the multiple order business of 5D element started from this prototypical compound, barium 2 sodium osmium O6. And firstly, in 2007, strange magnetism was found in this compound. This compound contains osmium 7+, which has 5D1 electronic configuration. And this is a magnetic insulator with a ferromagnetic moment of 0.2 mu b. This saturation moment is rather small for localized ferromagnet, but apparently too large for canted antiferromagnet. And strange thing is found in the magnetic anisotropy. Here, the angle dependence of magnetization. So this compound shows maximum magnetization when the applied magnetic field is around 110 direction. So simple random theory predicts cubic anisotropy favors 111 or 100 anisotropy. This observation is incompatible with the simple expectation. Then Professor Gan Chen made theory, including the electric quadrupole interaction between the transition metal site. And he proposed that there is a quadrupole order above the magnetic transition. And so this compound shows ferromagnetic moment, but he predicts that is canted antiferromagnet with unusually large canting moment. That's his prediction. And this prediction have been beautifully verified by Professor Mitrovich's group work. And this is the spectra of sodium-23 NMR. So we have single peak at the paramagnetic phase. But in the magnetically ordered phase, we have triplet. This means we have internal magnetic field. And the important thing is we have two sets of triplet. That means we have two equivalent sodium sites in it. So this is not simple ferromagnet, but antiferromagnetic order there. So this is, and also to have significantly large uncompensated magnetization, we should have large canting angle. So this is completely consistent with what Gan Chen predicted. And furthermore, we have this strange spectrum, which is different from paramagnetic phase and magnetic order phase. This distorted and split peak indicates the cubic local symmetry around sodium is broken, which means there is some anisotropic distribution around the sodium ion, which is again consistent with the existence of quadrupolar order. So this observation is quite encouraging for us because there should be, so the multipolar order indeed exists in 5D transition metal oxide, and there should be more. So then we started to look for another candidate. And again, we have double perovskite. Maybe some of them think why they are doing only on double perovskite. But this compound is perfect platform to search for multipolar orders. One thing is the high symmetry around transition metal site. So as Professor Gowling said, they focused on cubic because of frustration. But I also looking into cubic system, but slightly different reason. So if we have perfect octahedra around transition metal site, so that will not further split T2G level. So we can preserve J effective 3 half state. So we can have multiple degrees of freedom. And the other thing is we have moderately long distance between transition metal atoms. Since 5D transition metal have relatively spatially expanded orbital, so if we have a simple perovskite structure, that compound will be just boring paramagnetic metal. So by separating them moderately, we can enjoy localize the character of 5D transition metal element. That's the reason. And yeah, again, also we switch osmium 7 plus to rhenium 6 plus because we have many choice to study. And thanks to all these work, including Professor Gowring's group, we know the physical property of some of them. And among them, of course, I am focusing on cubic symmetry at room temperature. And now, as already presented by Professor Gowring, I'm interested in this compound. So this compound shows ferromagnetic behavior, but saturation moment is 0.3 μV, which is very similar to that of osmium double perovskite. And also they found this broad feature about the magnetic transition. So it must be something. So we are very excited with this result and started growing single crystal of this compound. And finally, it's very difficult to grow single crystal of double perovskite, but finally I grown small single crystal, but it's enough to detect quadrupole order. Yeah, let me start from the electronic state of this compound. So the spin orbit entanglement in this compound can be seen in magnetic susceptibility. So this compound shows ferromagnetic behavior below 18K, and this compound is insulator. So it follows Curie-Weiss behavior in the paramagnetic phase, and by fitting this curve with Curie-Weiss law, we can obtain effective magnetic moment, and that is 0.68, which is actually very small compared with S1 half. So we expect 1.73 μV. And this is because we have cancellation between spin momentum and orbital angular momentum. So this large reduction of effective moment is indication of spin orbit entanglement in this system. And more recently, I'm working with Yeonjun and Felix in Toronto, and they performed the resonant inelastic X-ray scattering experiment to see the excited state. Here we see the very faint easy state, and the separation is 5 eV as we expected. Furthermore, this is a ground state, but there is splitting of the ground state, which means T2G level split into J3 half and J1 half state. And the magnitude of splitting is 0.5 eV as we expected from spin orbit coupling. So now we confirmed J3 half state is realized, indeed realized in this compound. Then we performed resonant X-ray scattering because the moment size is small. We thought it is maybe impossible to detect by our neutron diffraction experiment. So now we have a single crystal. So we performed the resonant X-ray scattering and see this magnetic intensity. So usually X-ray cannot detect magnetic reflection because the intensity is too small. But by utilizing the resonant enhancement, we can detect magnetic reflection by X-ray. So as expected for a magnetic peak, we see huge enhancement at the resonant energy. Then the superlattice intensity start to increase at magnetic transition temperature. And the propagation vector was determined to be 001, which means we have ferromagnetically aligned spin on 001 plane, and that's stuck antiferromagnetically. But again, we have considerably large saturation moment. So that means we have large canting. So this unusual magnetic structure was formed in barium-2 magnesium radium-06. And let me see the macroscopic physical property around TQ. So I magnify the inverse susceptibility around TQ. We clearly see some kink in the inverse magnetic susceptibility at this transition. So that means we have some electronic transition. But still, this follows Curie-Weiss law. That means magnetically paramagnetic. And also, we have this large peak in the heat capacity and release huge amount of entropy at this point. So it is very plausible. This TQ transition is quadrupole order transition. Then we try to detect by diffraction experiment. So generally speaking, quadrupole order is an isotropic distribution of charge, so which will induce lattice deformation through electron lattice interaction. So if the charge distorted like this triangle, by detecting this triangular shaped lattice, we can tell what kind of quadrupole order exists in it. And a possible quadrupole moment coupled with unique lattice distortion. So if we can perfectly detect the lattice distortion, this should be very small. But if we can detect any kind of quadrupole like this. So as we expected, the lattice distortion was extremely small. So we see the peak splitting and also appearance of superlattice reflection. But the tetragonal distortion is only 0.09%, and superlattice reflection intensity is very, very small. But anyway, we could detect this structure change at TQ. So this is the temperature dependence of tetragonal distortion, and this is the temperature dependence of superlattice intensity. As clearly seen, the structural change occurs from TQ. So those indicates there is some structural transition at TQ. And from the extinction rule, we decided the space group, a low temperature space group, to be P42 over NMN. So here, as a result of structural analysis, we realize what kind of structural distortion occurs in this compound. So at high temperature cubic phase, we have regular octahedra. But at low temperatures, the octahedron elongated in the, around the c-axis. And at the same time, perpendicular to c-axis, the octahedra is distorted in rhomboid form. And this elongation is uniform, but the rhomboid distortion is something like this. The top layer, purple layer, we have uniform distortion along this direction. But the second layer, orange octahedra, distort orthogonal direction. So this kind of antiferroic stacking was realized. And we can decompose this distortion into the normal mode of octahedral distortion, which is called EV and EU. So those two coupled to these x squared minus squared and 3z squared minus r squared quadrupole order. So then this rhomboid distortion of octahedra produces the intensity of superlattice peak. So we can trace the development of distortion from this data. And also the elongation of octahedron produces cubic to tetragonal transition. The tetragonal distortion is directly connected to this mode. And by quantitative analysis, we obtain the amplitude of quadrupole moment. So this quadrupole moment is dominant component. And x squared minus y squared quadrupole order stack alternately. That means antiferroic ordering of this quadrupole moment and ferroic ordering of this moment with 1/4 of intensity. So this is the conclusion of the synchrotron X-ray diffraction experiment. Then we observe quadrupole order in this compound. And more recently, my colleague Ivica and Jean-Louis and Henrik performed resonant X-ray scattering. This is more direct evidence for quadrupole order in this compound. So the quadrupolar will rotate the polarization of incident X-ray. So by detecting the polarization angle dependence of outcoming X-ray intensity, we can say what kind of quadrupole order exists in it. So they beautifully done this experiment and found that the dominant x squared minus y squared orbital exists in this compound. Now we know we confirmed quadrupole order in this compound. Then we are interested in the interaction between them. So how can we detect the interaction between them? Then we employed ultrasonic measurement. It's a really powerful measurement to detect the interaction between quadrupole moments. So this is done with Dr. Imajo and Toshi Muroi in the audience. So experimental setup is as follows. We have sample and attach thin ferroelectric device, and by applying acoustic current, the ferroelectric device vibrate and produce ultrasonic, propagating the sample. Then on the other hand, we have another ferroelectric device which will convert ultrasonic to AC current again. And by changing the configuration of crystal orientation and propagation direction, we can produce many kinds of local distortion in the material. So as I have already told, that each unique lattice distortion coupled to quadrupole moment, so we can detect the fluctuation of quadrupole moment above the ordering temperature, something like magnetization measurement. So this is the result. So usually the material become harder and the elastic constant increase at low temperature. This is a usual behavior. But in this case, we saw clear softening toward TQ. So this means quadrupolar fluctuation increase toward the transition temperature of quadrupole order. So here I show the elastic constant coupled to gamma 3. I mean the detected quadrupole order, quadrupole moment. So this clearly shows softening toward TQ, and after them, it shows hardening. It clearly shows there is quadrupole order. And this is something like Curie-Weiss law. We are detecting the fluctuation of quadrupole order moments. So we can analyze this softening by Curie-Weiss law. But apparently, this curve is too steeply dropped. So we cannot express by only one Curie-Weiss behavior. So instead, we have two Curie-Weiss components to fit this softening. Actually, this is just preliminary fitting, but we have this negative Weiss constant at high temperature fitting, and close to TQ, we have ferro interaction between quadrupole moments. So this is somehow consistent with our observation in X-ray diffraction experiment. We saw the coexistence of antiferroic order and ferroic order. And another interesting thing is we checked the different kind of elastic constant, and this C44 mode coupled with gamma-5 type quadrupole moment. And we also saw this softening toward TQ and hardening above that. So this also, some quadrupole fluctuation exists above the TQ. But the magnitude of softening is rather smaller compared to this one. That means, we think that means this is not the primary order. Anyway, now we know the interaction between them. So we put our barium to magnesium rhenium O6 into the electronic phase diagram. So we have quadrupole order and large angle canted antiferromagnetic order. So we are somewhere around here. So there is some other phase exists. So we are wondering if we can control this parameter somehow and investigate other electronic phases. So first we think about the chemical pressure effect. So here I listed barium 2B rhenium O6 with different B cations. And by changing the ionic radius of B cations, these are of course isoelectronic and also isostructure at room temperature. So by changing these B cations, we can control the lattice constant, which should tune some interaction between them. And some of them, the physical property have already been known. So this magnesium one and zinc one shows ferromagnetic behavior at low temperature, but calcium one only shows usual antiferromagnetic behavior. So first, I'm interested in what's going to happen in between them. And so this compound is surprisingly similar to magnesium one. So it has kink in the inverse susceptibility, and it clearly shows some different phase transition at the temperature above magnetic transition temperature. And here we measure the thermal expansion. So it shows clear anomaly at TQ, which means we may have some structural transition here. From these results, we think maybe cadmium shares the same electronic ground state as magnesium one. So it should be noted that this compound shows another phase transition at 170 K. I don't think this is related to electronic structure. So as Professor Gowling explained, the perovskite compound tend to have such kind of structural transition because of the mismatch of cation and anion size. So some of them without any d electron shows this kind of cubic to monoclinic transition. And in this compound, this compound is already tetragonal phase above the TQ, but it clearly shows some transition at TQ. So this small structural change is nothing to do with electronic transition in this compound. So now we are interested, we go into more closer in between ferromagnetic phase. Okay. So I totally skipped this part. Okay. Okay. So I try to tune the phase try to tune the electronic phase diagram and found this phase diagram in the solid solution, and also done with physical pressure experiment. So now let's talk about metallic compound. So this is related to the concept of spin-orbit coupled metal. So film surface is somehow unstable against any kind of interaction. And Professor Liang Hu proposed the concept of spin-orbit coupled metal. So if the strong spin-orbit coupling is exerted on a film surface, it shows spontaneous inversion symmetry breaking and forms some kind of exotic multipole. That's the proposal. And this pyrochlore oxide is the most promising candidate for this spin-orbit coupled metal. And this compound is famous in its superconductivity. It is the first superconductor in pyrochlore oxide and studied intensively 20 or 25 years ago. But it also shows very interesting structural change. At high temperature, it's regular pyrochlore structure, but it shows inversion symmetry breaking at around 200 K. And at that time, the Pauli paramagnetic susceptibility drastically decreased, which means it shows some electronic structure transition. But the structure distortion is so tiny, so nobody knows the low temperature exact structure of this compound. Then we decided to grow high quality single crystal to detect the structural change. So the structural change is really crazy. So here I represented, here is a representative diffraction pattern of this compound. So at a high temperature, we have cubic phase, and the below inversion symmetry breaking, we have tetragonal phase. And here we discover new phase. Even though people working intensively for 20 years, nobody observed this phase. But we found this orthorhombic phase in this very narrow region. And so this orthorhombic phase was found between phase 2 and phase 3. At lowest temperature, we again have tetragonal phase, but interestingly, you see the intensity ratio flip this phase 2 and phase 3. This means we have elongated unit cell in phase 2, but this is compressed in phase 3. And there is almost no thermal expansion. All these indicate this structural change is induced by some electronic instability. And since the inversion symmetry breaking is second order transition, we can understand this phase transition in terms of group space group relation of space group. The phase 1 and phase 2, 3 is connected by EU symmetry order parameter. And based on this symmetry argument, Hayame et al. Considers a possible electronic order below this transition. So they propose the electric toroidal quadrupole order and magnetic quadrupole order. But of course, this compound is paramagnetic, non-magnetic. So the remaining possibility is electric toroidal quadrupole order. And EU order parameter allow this kind of structural change, but it's very difficult to see. So let me explain what is electronic toroidal quadrupole. So here, red arrow shows the shift of rhenium ion from the regular position. So it's easier to understand in phase 3. We have this kind of displacement, twisting displacement in this direction. And this twisting displacement of rhenium atom induces the different distribution of electronic charge and induces toroidal moment along this direction. And by doing a similar way, we have Z square type toroidal order in this compound and X square minus Y square toroidal order in this compound. And this kind of toroidal order will produce a spin momentum rocking on the Fermi surface and will produce some exotic response by flowing current. And other interesting thing is superconductivity. By applying pressure, we can suppress that electronic toroidal order. And as a quantum critical point, the superconductivity shows different behavior as ambient pressure phase. So here, upper critical field enhances like 10 times. And the other time, so at low pressure, we have this coherence peak indicating of conventional superconductivity. But at around this region, we lose coherence peak, indicating some unconventional superconductivity appear at that point. So, and also we are searching for another candidate spin orbit coupling metal. So this concept is very generic for heavy transition metal elements. So we believe there are still some other compound hosting exotic multipole in itinerant system. So sorry for time. Okay, that's all for my talk. Thank you very much.